Hello everyone, I'll be solving problem 1.31 from my thermal physics textbook by David Schroeder. So problem 1.31 is imagine some helium in a cylinder with an initial volume of 1 liter and an initial pressure of 1 atmosphere, and then somehow the helium expands to 3 liters in a way that pressure also expands in direct proportion to it. So I'm going to draw real quick just a little simple image of this. So I'm going to draw me a little cylinder. And then I'm going to have some piston. Then I'm going to draw another the final cylinder with this. So this will be PF and volume F and pressure F, and this is P naught and V naught. So the cylinder goes from this image to this image over here. And so for part A, which this question is asking for a graph, sketch a graph of it, I want to say P's up here on the Y, and then volume is going to be on the X. So if volume starts here and ends here, and pressure starts here, how does it get, what's the graph of it look like? Well, since it's in direct proportion, I want to say as volume rises, so does pressure, so it's going to look very much, have a linear positive slope. And so in order to do the rest of these, I want to do a little assumptions that'll help me with my calculation. So I'm going to assume this is an ideal gas. I'm going to have 1 mole of He gas, helium gas, and then I'm also going to assume temperature is constant, because otherwise these equations it's very complicated. So I want to say T is going to be around 300 Kelvin, simply because the initial conditions of the cylinder are very close to STP, and so I will continue to use that. So since I've done part A, I will now do part B, which is calculate the work. And so the work is the negative integral of pressure as a function of volume, dV from Vf from V naught. And so since this is an ideal gas, I can say PV equals NKBT and solve for P, and then plug that into this, and then do this integral, which I get as NKBT times ln of Vf over V naught. Now plugging in the numbers for this gives me 6.02 times 10 to the 23rd times 1.381 times 10 to the negative 23rd times 300 Kelvin times the ln of 3 over 1, which gives me a work of 2,740 joules. Let me make that a little better. So this is the work done on the gas here. Now part C wants me to calculate the change in the helium's energy content, but I can't do that yet because I don't know what heat, the amount of heat that has flowed into this yet. But I can do I can find out for heat that I can do, so I'm going to do D, which is U equals Q plus W, and solve for Q so I can get U minus W, and U is the number of particles times the degrees of freedom divided by 2 times KB times T minus 2,740 joules. And so this gives me 6.02 times 10 to the 23rd times 3 halves times 1.381 times 10 to the negative 23 times 300 Kelvin, I can't forget that. Oh, whoops, Boltzmann's constant is joules over K, so that's where that joules comes from. And I'm going to add joules over K here, minus 2,740 joules, which gives me a Q of 1,001 joules. So now I can do the change of U, so I can say change of U is equal to Q plus W and get 3,841 joules. Because all I'm doing here is just saying 1,000 plus 1,001 joules plus 2,740 joules. And so that gives me this for the change of that. And then for just what I might do to cause the temperature to act like this, is just adding heat, which is what we have done to this system. Because if we don't add heat, the pressure will drop instead of rise when the volume increases. But since it rises, we have to add energy into this. We have to add heat to it. We have to add thermal energy. And so there you have it. Problem 1.31 solved.